Welcome to today's reading session, everyone. I'm Avinash, and I'm part of the ongoing cohort from Bangalore. And the paper we are going to review today is Rethinking ImageNet Pre-Training. So, as the name says, this paper is a study on pre-trained models and its alternate, which is training models from scratch. So here we have the agenda. List of topics we'll be covering. We'll get started by quickly discussing what transfer learning is and how the pre-train and fine-tune paradigm works. There are different modes of training which depend on whether or not we use pre-learned weights. We then get to the introduction of the core part of the paper, which is training neural networks from scratch without using any known feature representations and using random initialization instead. There was already some work done on this topic. We'll talk about those results as well. We'll see how normalization plays a critical part in training models from scratch, and we'll see the convergence comparison between training from scratch versus pre-trained model training. The experiments were done on some baseline models with some specific settings. I'll talk about the results obtained using the baseline model and then talk about making enhancements to the baseline models for obtaining better results. And finally, we'll see how the availability of data, the amount of training data, is going to impact the results. So let's get started. It's hard to think of an industry that doesn't use deep learning at the moment. There has been a rapid progress of deep learning in the recent years. Availability of large amount of data along with computation has fueled this progress. There have been many well-known as well as novel methods which internally are responsible for the growth of deep learning. One of those is transfer learning. Transfer learning is the method of using the representations or information learned by one trained model by another model which needs to be trained on a different data and for a similar or different task. Transfer learning uses pre-trained models, which are nothing but models which are already trained on some larger benchmark datasets like ImageNet. This method has accelerated the progress and application of deep learning. Training a neural network can take anywhere between minutes and months, depending on the data and the target task. Until a few years ago, due to computational constraints, this was possible only for institutes and organizations. With the pre-trained models readily available along with other factors, that scenario has now changed. Using transfer learning, we can now build deep learning applications that solve several vision-related tasks much quicker than how it used to be. With recent developments past year, transfer learning is now possible for language-related tasks as well. All of this proves that Andrew Ng was right about what he said a few years ago, that transfer learning will be the next driver of ML commercial success. Here's an image which helps in visualizing few possibilities when training a model. The image on the right represents a model in which the convolution base of a trained model is frozen, and the bottleneck features obtained from it are used to retrain the further layers. This is a typical scenario with pre-trained models. The image in the middle here represents a model where except the yes, please.
We cannot see the images. We're still stuck on your first slide.
Oh. Is it still the first slide? Do you not see the ImageNet pre-training slides where we have three block diagrams?
It is still the first slide for me. Yes.
Okay. Okay, I'll try stopping the sharing and do it again. Can you see it now?
Yes.
Okay, thanks for letting me know. So I'll just repeat what I just said. So here in the image on the right represents a model where we have the convolution base of a trained model, which is frozen, and the bottleneck features obtained from it are used to retrain the further layers. This is what we normally do with pre-trained models. Whereas in the middle, the image represents a model where except the few initial layers, the rest of the network is trained. And the final model on the left represents training a model from scratch. This is what we'll discuss as we review this paper. So in the pre-train and fine-tune paradigm, the model training starts with some learned weights that come from the pre-trained model. This has become more of a standard now, especially when it comes to vision-related tasks like object detection and image segmentation. The other alternate is to train a model from scratch with random weight initialization, which is studied in this paper. ImageNet pre-trained models are very good at detecting high-level features like edges, patterns, etc. These models understand certain feature representations which can be reused. This helps in improving the convergence and is used in state-of-the-art approaches on tasks like object detection, action recognition, and image segmentation. But how good are these representations? The feature representations learned by pre-trained models are domain dependent. They learn from the benchmark dataset they're trained on. So can we really achieve universal feature representations by building much larger datasets? Like a pre-trained model which is trained on ImageNet only learns features that are related to the images that are present in ImageNet. So just by building much larger datasets than ImageNet, which cover broader categories, can we have better feature representation or anywhere close to universal feature representation? Some work is already done in this area where datasets which are almost 3,000 times the size of ImageNet are annotated. However, it is noticed that the improvements on target tasks scale poorly with the size of the datasets used for pre-training. It shows that by simply building much larger datasets, it doesn't always lead to better results on the target tasks when fine-tuning. To train a model from scratch, all the parameters or weights in the network are randomly initialized. The experiments carried out in this paper use mask RCNN as a baseline. This baseline model was trained on COCO dataset, both with and without pre-training, and the results were compared. The results often prove that by training the model for sufficient number of iterations and by using appropriate techniques, the model trained from scratch also gives comparative and close results to that of the fine-tuned model. So being used to the pre-trained models, training from scratch might sound non-trivial, time and resource consuming. Some prior research was done on this topic of training models from scratch instead of using pre-trained models. DetNet and CornerNet use specialized model architectures to accommodate training models from scratch. But there was no evidence that these special architectures have given any comparative results. In this work, the authors considered using existing baseline architectures with a couple of changes. One is to train the model for more number of iterations, and the other is to use batch normalization alternatives like group normalization and synchronized batch normalization. With this, the authors were able to match the accuracies of both methods. If models that are trained from scratch, if the models are trained from scratch without proper normalization, it can produce very misleading results, which might mean that training from scratch is not optimal at all. For vision-related tasks, the training data consists of images of high resolution. This means the batch size has to be adjusted accordingly to meet the memory constraints. Batch normalization works well with bigger batch sizes, but with high resolution images and memory constraints, model training has to limit its batch size to a smaller number. This leads to bad results with batch normalization, as batch normalization is very dependent on the batch size. The larger is the batch size, the better results batch normalization gives out. So to avoid this, group normalization and synchronized batch normalization are used in the experiments that are done in this paper. Group normalization is independent of the batch size. So it doesn't matter whether the batch size is smaller or bigger, group normalization still gives out decent results. Synchronized batch normalization, on the other hand, is a workaround. It uses multiple devices. This increases the effective batch size. And by doing so, it avoids smaller batches, which enables training models from scratch. The fine-tuned models get kind of a head start, as the pre-trained model already learned low-level features, the high-level features. That means the models trained from scratch cannot converge as fast as the fine-tuned models. Though this makes fine-tuned models better, one should also consider the time and resources it takes to pre-train a model on large benchmark datasets like ImageNet. When pre-training on ImageNet, over 1 million images are trained for many iterations. So for the random initialized training to catch up, the model needs many training iterations. The image here summarizes the number of training samples seen in both cases, with and without pre-training. Depending on the target task, the samples can be images, instances, or pixels. For a segmentation task, the model works at the level of pixels, whereas for object detection, what matters is the instances of objects in each image. We see that except in segmentation or pixel level task, training from scratch takes substantially fewer number of training samples. The numbers here consider both pre-training and fine-tuning. So here, if we observe, we have the total number of images that are considered when fine-tuning, which includes both ImageNet, the big gray bar here represent ImageNet data, and the green one represents COCO data, which we'll be using for all the experiments in this paper. Whereas the one in purple represents the data which is used when training a model from scratch. So if we are considering image samples here, the number of samples that are used for when training from scratch are much fewer when compared to the number of images that are seen when fine-tuning is considered. The same is seen in the instances example as well for object detection. Only when it comes to pixels, we see that the number of instances are close for both the cases, with pre-training and without pre-training. So these are the experiment settings, the architecture and the hyperparameters that are used. As discussed earlier, the experiments use mask RCNN with ResNet and ResNext architectures as a baseline. Group normalization or synchronized batch normalization are used for normalization methods. The model is trained with an initial learning rate of 0.02, and it's reduced by 10 times in the last 60K and 20K iterations respectively. The training data is flipped horizontally, and there is no test time augmentation which is applied on this baseline model. A total of 8 GPs were used for training. By training a model with these settings on COCO dataset with 118,000 training and 5,000 validation samples, the model trained from scratch was able to catch up in accuracy with that of a pre-trained model. Object detection and image segmentation are the two target tasks. Average precision for bounding box and mask are the metrics that were considered here. So as we can see in the plot here, the plot on left was trained with ResNet 101, and the normalization used in this experiment was group normalization, whereas the plot on the right shows results for mask RCNN with ResNet 50 and synchronized batch normalization. We see that, so the purple color, what we see here, represents a model which is trained from scratch with random initialization, and the gray one represents the model which is trained with pre-trained network. So a pre-trained network is taken and then it is fine-tuned on COCO dataset. So we see that when fine-tuning, the pre-training has some kind of head start here. In both the cases, with fine-tuning as the training methodology, the average precision starts with a value which is close to 20. Whereas when training from scratch, model starts with AP value of close to 5, which is pretty lower. And that's expected because with a pre-trained and fine-tuning methodology, you already have a model which is trained on some data. So it gets a good start. The spikes that you see here indicate different schedules. The authors in these experiments have run the same baseline model for different schedules, which is nothing but they have used schedules called 2x, 3x until 6x. So with each schedule, the number of iterations get increased. That is why we see for the last schedule here, which is 6x, we see that we see almost the accuracy value of the model which is trained from scratch is almost the same as that of the fine-tuned model. So these are the plots comparing the results of both pre-trained model and a randomly initialized model. The authors also tried making enhancements to their baseline model by adding scale augmentation during training, and also making changes to the architecture by adding cascade RCNNs and test time augmentation. By adding scale augmentation during training, better results were reported, and that's not surprising since data augmentation almost leads to a better accuracy. Similarly, using cascade RCNN and test time augmentation also improve the results. We see that with test time augmentation, models trained from scratch give better results than the pre-trained models. So here are two plots. The one on the left is with ResNet 50, and the other one is with ResNet 101. In the fourth enhancement here, where we have cascade RCNNs and both train and test augmentation, we see that the final results of both pre-trained models and the models which are trained from scratch are almost same. In fact, the model which is trained from scratch, the first bar here has a higher value of 48.6, whereas the model which is trained with, which is fine-tuned, has 48.3. So these are the results that were carried out after doing some enhancements like training term augmentation, using a different, modifying the architecture a bit by adding cascades, and using test time augmentation as well. So this was the most interesting part of all the experiments, that at least to me, that this is the most interesting part of the paper. The final experiment was trying different amount of training data. While the first interesting result from this work is that we can get comparable results even with models trained from scratch, the other surprising discovery is that even when the data is less, training from scratch can still yield close results to that of the fine-tuned models. So here we see, when working with only 1/3 of the whole COCO training data, that is close to 35K images. Here in one of the experiments, they have taken only 35K training images out of some 115K total training images. The experiment shows that the fine-tune approach start overfitting. You can see that here. So in this plot, a fine-tuned model was trained on COCO subset data of 35K images. And we see that after certain iterations, it starts overfitting. So that shows that ImageNet pre-training doesn't automatically help reduce overfitting. So even with ImageNet pre-training, when you have a certain number of training samples, there is a chance that the model overfits. But despite less data, training from scratch still catches up with fine-tuned results. That is what we see here in the middle plot. Even when the training images has come down to 35K from somewhere like 115K, the model which is trained from scratch here, it still catches up and gets an accuracy which is almost the same as that of a fine-tuned model. And in the rightmost plot here, we see that the same experiment was done with 10K images as well. So with 1/10 of training data, the training from scratch shows the same trend. So what if we try with much lesser data? Like, we have tried with 1/3 of data, we have tried with 1/10 of the whole COCO data set, which is only 10K images. Can we try with 1/100th part of the whole training data, which is only like 1K images? So that was also tried. When only 1K images are used, training from scratch still converges, but this time it is pretty slow. But the critical part here is that it starts producing worse results than the fine-tuning model. So when only 1K training images are taken, the pre-trained models gave average precision of 9.9, whereas the model which is trained from scratch gives average precision of only 3.5. This is a sign that the model which is trained from scratch has overfitted due to lack of data. So in these experiments, when the training data has come so low that we are only taking like 1,000 training samples, that's where the authors have noticed the breakdown, where the model which is trained from scratch cannot catch up with the model which is fine-tuned with ImageNet pre-trained model. So that is all about this paper. These are all some of the things that that were experimented. Training from scratch on target tasks can be done without any special architectures. While some prior works were tried they did go with some special architectures, but they didn't show any evidence that even with those special architectures, they were able to produce results which are comparable to that of fine-tuned models. So when we are going with training from scratch, we just have to supplement that with training the model by for more iterations. So when we do that, we can get results which are very comparable and close to that of the fine-tuned models. The authors also noticed that with ImageNet pre-trained fine-tuning, the convergence speeds up initially, but that doesn't translate to the overall task performance. Though there is a good convergence which is noticed in the beginning, it is not always necessary that this converts into producing better performance results than training from scratch. And also, as we discussed before, for when the number of training samples comes down by a certain margin, ImageNet pre-training starts overfitting. Even the fine-tuned model tends to overfit. As said, the pre-trained models are very domain specific. So when a pre-trained model which is trained on ImageNet data can only learn features which it has seen from the images in the ImageNet, and also it is more specific to the kind of task for which it was trained, which in most cases is for object detection. So that doesn't always do well for tasks which are more related with localization. The paper nowhere claims that the pre-train and fine-tune approach is not recommended. Rather, I felt that this is an interesting study, especially because the pre-train and fine-tune paradigm is being used more as a standard procedure. And considering where all DL is being applied, which includes use cases for automobiles, health, retail, it is essential for the research to not only aim for novel and innovative methods, but also to study the existing methods in more detail. This would surely lead to better insights and new discoveries, which was the case with this paper. So that's what I had in this paper presentation. I'm open for any questions.